Hello dear students. So in this section, we'll be discussing the integrated rate equations for a zero order reaction and first order reaction. So you can see that there are different types of reaction depending upon the power of reactant. You can call it as zero order reaction. If order is equal to 1, then it is called first order. Order equal to 2, 3, etc. We can call it as second order, third order reactions, etc. So definitely we can classify them as zero order, first order and nth order reactions. So here we'll be discussing the integrated rate equation for a zero order reaction and also integrated rate equation for a first order reaction. And now we need to know what are integrated rate equations. So normally in order to calculate the overall rate means we have to integrate the graph that we have seen, like the instantaneous rate. And practically it is not possible to calculate the instantaneous rate of an entire reaction. So here, in order to overcome that practical difficulty, we'll be integrating the differential equations. Okay, that means you have like instantaneous rate is equal to minus dr by dt. So on integrating that value or minus dr by dt, we'll be getting the rate for the overall reaction. So here the integrate, or we can say that the differential equations are integrated. And now we need to know what some of the basic equations of integration. Okay, so before starting that integrated rate equation, let me give you some idea about the integration where you need to learn some of the formulas of integration. For example, see integral dx. Integral dx is equal to x plus c, where c is the constant of integration. So dx means it's a very small fragment of x. When all the dx are integrated, you'll be getting the value of x. Or we can say that example, or integral dt. Integral dt will be equal to t plus c. Then integral dx divided by x. Integral dx by x, that will be equal to natural logarithm of x, ln x. And natural log of x, now if you want to convert into log x, you have to multiply with 2.303. So that is equal to 2.303 log x. And integral a constant into dx, that will be equal to constant into integral dx. That means the constant should be taken outside the integration. You might have learned all this in physics. Yeah. So these are the basic equations that we'll be using in integration. And then we have an equation for a straight line. The equation for a straight line is y equal to mx plus c. Now this is called the integration or with the equation for a straight line, where y represents the y coordinate, x will be representing the x coordinate. Now m is called the slope of the straight line. M is called the slope of the straight line, and c is called the y-intercept. Y-intercept means the point where the straight line touch the y-axis. Suppose if you want to plot the graph for the equation y equal to mx plus c, very simple. Now on this will be the y coordinate and this will be the x coordinate. And now the straight line, you'll be getting a straight line. Either it will be a positive slope or it can be a negative slope. If this value of m, if it is positive, then the graph will be from a lower end to a higher end. So this will be the nature of the graph. So this is called a positive slope. And if it is the negative slope means it will be from a higher end to lower end. Okay. So here, let me take a positive slope now like this. Okay. Now here the straight line, this is the point where the straight line touch the y-axis, and that is called the y-intercept c. So here the value of c will be from 0 to that particular point. And now the slope, now this is called the slope of the straight line. Slope is equal to, and if it is x and this value is y, we can say that slope is equal to x divided by y. Or that is also if this angle is theta. If this angle is theta, slope will be equal to tan theta. Slope will be equal to tan theta. So this is how we are finding the slope of a straight line, then the y-intercept. So these are some of the basic idea that you should have in this chapter. Now we'll move on to the integrated rate equation. Now let's consider an integrated rate equation for a zero order reaction. Okay, one. Now we'll move on to integrated rate equation for a zero order reaction. Now you consider a zero order reaction R giving P. Okay, consider a zero order reaction R giving P. So here, for a zero order reaction means the rate will be independent of the concentration of reactant. Yeah, because rate is equal to, I can say that rate is equal to K into R power 0 because it is a zero order reaction. So rate is equal to K into R power 0. Or rate is equal to constant because R power 0 is equal to 1. That means a zero order reaction is the one in which the rate is independent of the initial concentration of the reactant. And also we know that the instantaneous rate is equal to minus dr divided by dt. So we got two equations. Rate is equal to, or rate equation is K into R power 0 and instantaneous rate is equal to minus dr by dt. Let it be equation 1 and let this be equation 2. Now on comparing equation 1 and 2, we can say that K into or minus dr by dt, minus dr divided by dt, that will be equal to K into R power 0. Because both are rate, because K into R power 0 represents the rate and minus dr by dt also represents the rate. So you are getting minus dr by dt is equal to K into R power 0. And you know that R power 0 is equal to 1, so you can write it as minus dr by dt. Minus dr by dt is equal to a constant K. Or minus dr, okay, we can write minus dr, therefore minus dr is equal to K into dt. Or dr is equal to minus K into dt. Is it clear? So we got an equation dr is equal to minus K into dt. Let me call this as equation 3. Next step, let us integrate that equation. So that means integrating, okay, integrating equation 3. On integrating equation 3, we'll get integral dr. Okay, so I'll write integral dr is equal to minus K into integral dt. Integral dr is equal to minus K. That means minus K another constant, so we'll take outside the integral side minus K into integral dt. And now you know that integral dx integral dx is equal to x plus c. X plus an integral constant. So I'll write integral dr will be equal to concentration of R. You have a constant, we'll keep it there. That is equal to minus K and integral dt, that will be t plus another constant. So here you are having a constant C1 and here you'll be having a constant C2. But we'll do one thing, we'll write that both constants together. Okay, we'll write it as plus a constant, okay, plus a constant C, plus C I'll write. So we got minus R or R equal to minus KT plus C. Now this is the equation, let me call it as equation 4. So here R represents the concentration of the reactant at time t. So at time t, that means we started the reaction with initial concentration, and at a particular time, the concentration of reactant is reduced. Okay, that concentration of reactant is reduced. So initially when time is 0, the concentration, let it be R0. And at time t, the concentration is reduced to R. So here all the terms are clear, but we have an integral constant, that is C. To find the value of C. Okay, now we need to know what should be the value that must be given for C. Now let me say to find the value of C. Now just imagine we started the reaction with the initial concentration of R0. That means when T is equal to 0. When T is equal to 0, the concentration of reactant was R0. Now at a time T, now the reaction have proceeded. We started the reaction, now we reached at a time T. Now the concentration is R. That means the concentration of reactant depends on time. When time is increasing, when you give more time for the reaction, the concentration of reactant will keep on decreasing. Again, if you move to another time, we call it as T1, the concentration will be another concentration, R1. So here, when time increases, the concentration of reactant will be keeping on decreasing. And at time T, and at time t, the concentration of reactant is R. So what about at time 0? At time 0, I can say that the concentration of reactant will be R0. Yeah, when time is 0 means concentration of reactant will be initial concentration, which we call it as R0. Now we'll do one thing. Now to find the value of C, you substitute when t is equal to 0. T equal to 0. When time is 0, that means we have just started the reaction, the initial concentration. The value of R will be equal to R0. That means we started the reaction. We started the reaction with the maximum concentration of reactant. And now at time t, the concentration is decreased to R. So if you go back, when the time is again t0 means, you'll be having the initial concentration itself. That means when time becomes 0, that means if you are going back, if you go in a reverse manner, when time becomes 0, the concentration of reactant will become the initial concentration. So I'll make this t0. Okay, now that is equal to minus k into 0 plus C. When time becomes 0, instead of R, I can write it as initial concentration R0, which means C will be equal to R0. Now you substitute the value of C in equation 4. Substituting the value of C in equation 4, you'll be getting concentration of R is equal to minus KT plus concentration of R0 or R0. Concentration of R is equal to minus KT plus concentration of R0. This indicates that the concentration, that means the value of R0 is the initial concentration, and at time t, the concentration is reduced to R. We'll take one example. Suppose initial concentration, let it be 10 molar. And after a particular time t, like 10 seconds, or we'll make another value, like if it is 10 seconds, don't get confused, like after 3 seconds. After 3 seconds, let the concentration be reduced to 3 molar. That means initial, so the amount of substance reacted will be 10 minus 3, that is equal to 7 molar. So here R0 means the initial concentration. Then R will be the concentration at the time t. So this t and R will be depending with each other. When you increase the value of t, the value of R will be decreased. Okay. Now here, this equation is called integrated rate equation. The above equation is called integrated. Okay, integrated rate equation. For a zero order reaction. By heart the equation. Okay. By heart this reaction. R is equal to minus KT plus R0. So we started the reaction. Okay, you can go through the video once again. So you can see how we are integrating that equation, and we got R is equal to minus KT plus R0 or R0. And this equation, if you see the equation, you can say that this equation is of the form y equal to mx plus c. This equation is of the form y equal to mx plus c. So now we'll see how to plot the graph for the above equation. So we got R is equal to concentration of R is equal to minus KT plus concentration of R0. So comparing with the equation y equal to mx plus c. Y equal to mx plus c compare பண்ணும்போது, now listen, if you try to plot the graph, on y axis you should be having concentration of R. On x axis you'll be having the time. And now see the value of slope. The value of slope is minus k. That means it is a negative slope. That will be a negative slope. So here the slope, the straight line will be like this with the negative value for slope. And here the value of slope is equal to minus k. And what is y-intercept? Y-intercept means that will be represented by C, and y-intercept will be equal to R0. That means the concentration of reactant at time t. So here this value, this distance is called R0, which is called the y-intercept. Slope is equal to minus k. So we got R is equal to minus KT plus R0. And now if you rearrange this equation, so R is equal to minus KT plus R0. R is equal to minus KT plus R0. So I'll get KT is equal to R0 minus R. KT is equal to R0 minus R. So R0 means it is the initial concentration and R is the concentration at time t. So R0 minus R. Initially, you have 10 molar concentration. Now at time t, you are having 7 molar. That means amount reacted will be 10 minus 7. So 10 is R0 and 7 is R. So R0 minus R represents the amount of substance reacted by time t. So we can say that for a zero order reaction, the amount of substance reacted, that is reacted by time t, that is equal to K into T. Because the amount of substance reacted will be equal to R0 minus R. The amount of substance reacted will be equal to R0 minus R, and that will be equal to K into T. So rate constant, if it is given, and time for a zero order reaction. Suppose now the rate constant 2.8 into 10 raised to minus 3. Let it be the value of K, and time is equal to 30 seconds. Then the amount of substance reacted will be 2.8 into 10 raised to minus. That means that will be equal to K into T. And if a reaction is A giving B, the amount of substance reacted is equal to amount of substance product left, that is formed. So amount of substance reacted is equal to K into T, and amount of substance produced also will be equal to K into T. So this equation, you can take down this equation, Kt equal to R0 minus R, which represents the amount of substance which is reacted. And also now we'll make an equation for K, the rate constant. Now listen, the rate constant K is equal to R0 minus R divided by T. The rate constant K for a zero order reaction, will be equal to R0 minus R divided by T will be the value. So is it clear? So this is how we are finding the integrated rate equation for a zero order reaction. Now we have to take some of the examples for a zero order reaction. Now in case of zero order reaction, I'll give you some examples. So the first example is like the decomposition of ammonia on hot platinum surface. Okay, now example for a zero order reaction. First one, decomposition. Okay, decomposition of ammonia of NH3 on hot platinum surface. So the reaction will be 2NH3 giving N2 plus 3H2, and the temperature is around 1170 Kelvin. And the reaction takes place on platinum surface. So decomposition of a gas on a solid surface is an example for a zero order reaction. So we can say that rate of this reaction is equal to K into concentration of NH3 raised to 0. Because it's a zero order reaction, so rate is equal to a constant. And now why the rate of the reaction is independent of the concentration of reactant? The reason is that at high pressure, the platinum surface will get saturated with the gas molecule. It will be saturated. That means at high pressure, the surface of the catalyst will be saturated. That means all the surface will be occupied by the ammonia molecule. A further increase in pressure, thereafter, if you increase in pressure, there will be no effect on concentration of it, because already the solution, that's the surface area, is getting saturated. So a further increase in pressure will not make any change in the decomposition reaction. So the surface area will be saturated at high pressure. And we can say that there will be no further change in if you increase or decrease the pressure. And we'll give one more example. Next example is, so first one is decomposition of ammonia on hot platinum surface. Then we can take the decomposition of hydrogen iodide. Second example is thermal decomposition of hydrogen iodide HI on gold surface. Okay, now the reaction will be 2HI giving H2 plus I2. 2HI giving H2 plus I2 will be an example for another zero order reaction. And here also we can say that the surface area will get saturated at high pressure. So a further change in pressure will not make any further decomposition of that particular material because surface area will get saturated. Okay. So these are the points that you have to remember in zero order reaction. Okay. So hope it is clear. Now go through that equation once again and make the short notes on all the additional equations and see. So this is the printed form, like you can consider the reaction what I have already explained. So this will be the graphical representation of zero order reaction. Hope it is clear for you. Go through the equation once again. Study that how to integrate and by heart the reaction. Okay, R equal to minus KT plus R0. And now we have to go for the next one, integrated rate equation for a first order reaction that will continue in the next session. Hope this topic is clear for you. Thank you.